Welcome to the central force problem. Today we are going to discuss about the Laplace-Runge-Lenz vector. To begin this discussion, we start from Newton's second law written for a central force, and we simply take the cross product on both sides with the orbital angular momentum and carry out the calculation. This is very straightforward. It leads to the expression here. And now we need to evaluate the dot product between the radius and the radius vector and the radial velocity. This is a straightforward procedure which we have applied previously as well, or it can be seen immediately since it is clear that the radial velocity is always tangent to the radial vector, so the dot product here is just the scalar product of the magnitude of the two vectors. And having this expression, we can just take the total derivative with respect to time of the cross product here, and the evaluation leads to this result. Or furthermore, if we factor things out again and do the if we do the trivial integration here, we obtain this this expression. Now, if in this result we apply the condition for the force to vary as the inverse square of the distance, then we obtain an equality between two terms under the derivative operator. And as such, we are speaking in effect about a new conserved quantity, which is the vector A simply equal to the difference between the left and right hand side. And this is the Laplace-Runge-Lenz vector. It is immediately clear that this vector is perpendicular to the orbital angular momentum, which is seen by simply calculating its dot product with L. And furthermore, if we take its dot product with R, so this would be its projection on the radius vector, we obtain the result here. Now, in this expression, if we evaluate the first term, it turns out that this is just L squared, and as such, and the magnitude of A times the cosine of the polar angle is the quantity here. Or if we solve this for 1 over r, in effect we find our way back to what is essentially the orbit equation. So what we see from here, for instance, is that the Laplace-Runge-Lenz vector always points to the perihelion. It's given this expression, it's always located in the plane of the orbit, and from the orbit equation here, we see that its magnitude is given by the product here. So, for the Kepler problem, we have found that the constants of motion are the orbital angular momentum, the Laplace-Runge-Lenz vector, and the total energy. So 7 conserved scalar quantities, which are the free components of each vector and the energy. However, for motion in having 3 degrees of freedom, the total number of independent constants of motion is 6, which could be, for example, the initial conditions for position and velocity components. So only 6 independent quantities can be present here. And furthermore, as at least one such quantity must relate the position of the particle on the orbit, it follows that only 5 out of these 7 constants are independent, because as we have discussed previously, one of them is irrelevant for the actual equation of the orbit, as it simply relates the initial position of the particle on the said orbit. And as such, the free quantities listed here must be connected through two relations. One of them is the equation 3.83, which is just the perpendicularity between the Laplace-Runge-Lenz vector and the orbital angular momentum. And the second one can be found from taking together the result 386 with equation 357, and it gives the squared magnitude of the Laplace-Runge-Lenz vector in terms of the squared magnitude of the orbital angular momentum and the value of the total energy. Now, an interesting result can be derived as follows. If we write the definition of the Laplace-Runge-Lenz vector and then write the orbital angular momentum explicitly, and we also decompose the radius vector in its Cartesian coordinates, we find the expression here. So this is just the definition of the Laplace-Runge-Lenz vector, but written in Cartesian coordinates. If we now take the cross product between the orbital angular momentum and the Laplace-Runge-Lenz vector written in such a way, the result is the one given here. It's trivial to evaluate it. And now we also choose the perihelion position, which is the point to which towards which the Laplace-Runge-Lenz vector is pointing, to be located on the x-axis. So in effect, the value of A is the one given here. Then if we put these things together, we obtain the expression here, and if we solve it for the linear momentum, we find this very simple result, which in effect is just a circle of radius mk divided by L, which is displaced on the y-axis by the ratio of capital A to L. So this is a locus curve known as the hodograph. This result finds application in various problems related to orbital dynamics, and we can consider the simple example here. So let us assume that a meteor strikes the Earth with speed v at an angle phi or phi with the zenith. And far from the Earth, the meteor speed was v prime, and it was moving at an angle phi prime with the zenith. The effect of Earth's gravity being to pull it into a hyperbolic orbit intersecting Earth's surface. We are to find the initial quantities in terms of the impact ones and known constants. So the conserved total energy of the system when striking the Earth, the value is the one given here, and at very large distances where the potential goes to zero, it is given by the value here. So as such, we can write the initial velocity in terms of the impact velocity and Earth's radius through this very simple expression. To do the same for the initial angle, we first of all begin with the value of the angular momentum. Again, when impacting the Earth, the value is the one given here. It's the radius of the Earth times the impact momentum times the sinus of the angle between these two quantities. Now, initially, the orbit equation of the meteor is simply the one given here, which follows from the fact that r tends to infinity initially. So if we just write the orbit equation for an infinite radius, then we find that the theta prime is given by the value here. And then if we furthermore at this particular value of the angle, we just apply the formula we have derived previously for the linear momentum. We find this result, but for the y component, this is just the projection is simply p times the cosine of phi prime. So then what follows immediately, since we know the magnitude of p, because this is just m times the initial velocity, and then we can find the cosine of phi prime as the quantity here. And if we were to replace phi prime and the eccentricity, we would obtain just the result in terms of all of the known constants. Conserved quantities that, together with the angular momentum and the energy, define the orbit can be found for general central potentials, but they are rather peculiar functions of the motion. For non-closed orbits, r is a multivalued function of theta modulo 2 pi. In fact, it is an infinite valued function of theta, as given enough time the particle will trace out the entire available range. Hence, the additional conserved quantity will also be infinite valued. If r and theta are periodic with frequencies omega r and omega theta, if the ratios of the frequencies is a rational number, then the periods are said to be commensurate. Such orbits are closed. When the angular frequency is greater than the radial one, the orbit spirals about the origin as the distance varies between the apsidal values, closing only if the frequencies are commensurate. And in effect, this is something that we have seen multiple times through our various applications to all sorts of central potentials that are different from the Kepler potential. If the two frequencies are equal, the periods are degenerate and result in conserved quantities such as the Laplace-Runge-Lenz vector. This remains true for Hooke's law, where this condition leads to a conserved tensor of the second rank. Thus, the existence of such an additional simple conserved quantity is enough to indicate that the motion is degenerate and that bound orbits are closed. We will suppose now that there existed a magnetic singularity giving a magnetic induction field capital B equal with a measure of the magnetic charge B times the vector r divided by the cube of the radius. So it's an inverse square law force having as measure the magnetic charge B. And we will assume further that a particle of mass m and electric charge q moved in the combined gravitomagnetic field obtained here. Then Newton's second law would contain two terms. One of them is the simple gravitational term, and the other is due to the Lorentz force and contains the product between the electric and magnetic charge. Now, it is clear that because of this cross product, the overall force acting on the particle is non-central. And yet we can, starting from this expression, we can easily evaluate the time derivative of the orbital angular momentum, which is given here. And then we can also evaluate this double cross product immediately to be the one found here. Then, putting the two together, the time derivative of the orbital angular momentum is this quantity. And upon a straightforward integration, this is equivalent of the expression here, where this is just a mistype. It's not V, but B, the magnetic charge. So that the product of between the electric and magnetic charges carries over through the calculations. And then it is clear that from this expression that the quantity presented here is conserved, and we will denote this vector by capital D. Now, if we were to assume that this dynamics could somehow be simulated by a central force, then in this assumption we can take the we could take the time derivative of the cross product between P and D, using the fact that D is conserved, to find the result here, and then again to the the expression here. And now if we assumed further that this was an inverse square law force given by some force constant kappa, then putting these two together, we would find that the time derivative of this cross product is equal to m times k times the there's a derivative operator missing here, so this is the time derivative, this quantity. So the conclusion would be, once again, that we have a conserved vector which is analogous to the Laplace-Runge-Lenz vector, where the quantity d plays the role played previously by the orbital angular momentum. In summary, we have determined an additional conserved quantity for inverse square law central forces in the form of the Laplace-Runge-Lenz vector, and we have deduced its relations with the orbital angular momentum and the total energy. We have studied a few applications to orbital mechanics in the Kepler problem, and we have discussed the general implications of such conserved quantities. We have investigated the hypothesis of magnetic singularities considering conserved quantities similar to the Laplace-Runge-Lenz vector. And in the following, we will discuss scattering in central force fields. That being said, I want to thank you very much for watching the video. I hope you found it worth your time, and I will catch you later. Goodbye.